Here it is, guys. Video number 2 in the same day. I'm on a mad one, okay? The reason I'm doing 2 videos in one day is to celebrate, of course, it is Star Wars Day. May the 4th be with you. Are you ready for chemistry? I hope so, because we're going to go straight into it and have a look to see what we're up to. So, astenine is a group 7 and period 6 of the periodic table. The atomic number of astenine is 85. An isotope of astenine has 125 neutrons in its nucleus. Look at the table of information about this isotope and complete the table. So, step 1. How many electrons does it have in its outer shell? Well, that's easy because it's in group 7, so therefore it has 7 electrons. Number of occupied shells, again, that's easy because we know it's in period 6, and so therefore it has 6 occupied shells. Little bit trickier with what the mass number is. Remember, guys, the mass number is the number of protons plus the number of neutrons. So it's told us how many neutrons it's got, 125. It's told us how many protons it's got because it's told us the atomic number. So we add 125 to 85 and we get 210. And that's 3 marks. Oh my god, 3 marks? Yes, 3 marks, okay? On to the next question. And here it is. Okay, so we're back to group 7. We've got all our different group 7 elements on the left, and it's telling us our melting points and boiling points of each one. Now, all it's asking you to do is predict what the melting and boiling point of fluorine is going to be. So it's a bit of a tricky question, but actually, if you think carefully about it, it's really straightforward. Because all you got to do is look at the kind of trend in melting point. Obviously, we can see that it's getting lower and lower and lower and lower. And so we've just got to put something in that's going to follow that trend. So anything between minus 240 and minus 160 will get you a mark. Well, actually, it will get you half the available mark. Okay? The other bit, you have to do exactly the same with the boiling point. And here, anything between minus 200 and minus 80 will get you the mark there. So that's the first page done. Let's move it on. So, Zahir works in a laboratory. Lucky Zahir. The temperature inside the laboratory is 20 degrees. Predict the state of fluorine at 20 degrees C. Choose from solid, liquid, or gas. Okay, so what we have to say straight away is obviously it is a gas. And to get the full mark, we need to make sure that we say, because the boiling point is less than 20 degrees C. So we know it would have been turned into a gas. Easy mark, easy. Right, all the elements in group 7 have simple molecular structure. Which element has the strongest intermolecular forces? Of course, it is going to be astenine, which has got the chemical symbol AT. That is because it's got the highest melting and boiling point. That's kind of how we know it. Zahir predicts that chlorine will react to potassium acetate solution, KAT. He predicts that potassium chloride solution astenine, A2, will be made. Construct a balanced symbol equation for this reaction. So here we go. You ready for it? Remember, 2 marks. You get 1 mark for writing out the equation. 2nd mark is for balancing it. So we know that chlorine comes as a pair. It's a dimer, so it's Cl2. Then we get plus cat, potassium acetate, turns into potassium chloride and astenine. So obviously this isn't balanced, and the way that we're going to balance is we write down all the elements that we've got in our equation down the bottom, then we count up how many we've got. So we've got 2 chlorines over here, we've got 1 potassium, and we've got 1 astenine. On this side we've got 1 chlorine, 1 potassium, and 2 astenines. So obviously we've got a bit of an issue with balancing here. So what we need to do is we need to increase our astenine on this side. So we put a nice big 2 in front of this. So now we count them up again. We can see that we've got 2 potassiums, 2 astenines. So, oh dear, we're still not balanced. We're short a chlorine and a potassium on this side. So what do? We put a nice big 2 in front of there. which makes it up so that we've got a nice balanced equation for your second mark. Always remember, when balancing equations, we want exactly the same number of everything on one side as we do on the other, and we can't just put a little 2 in there or a little 3 in there. Absolutely no, we can't do that, because that changes what it is. You can only put the big numbers to say, look, I've got 2 potassium acetaldehydes, or I've got 2 potassium chlorides, not just the one. Okay, so just remember those things and you'll do just fine at your balancing symbol equations. On to the next page then. Here it is. A very large metal structure called the orbit was built for the London Olympics. Look at the picture of the orbit. The table shows information about some metals that could be used to make the orbit. So it's a very impressive structure. What metals have we got? We've got A, B, and C. Okay, loads of different information. You've got to start thinking about, well, what things do I want a big structure to be good at? Okay, so you've got to think about corrosion, because obviously it's going to be outside. You've got to think of its strength, because it's going to be this massive structure. Last thing you want to do is crash down and crush somebody. And so just have a little think about that. The question itself asks us to explain with reasons, okay, so with reasons, which metal, A, B, or C, from the table would be best to make the orbit, okay, so you've got to kind of justify your decisions here. 2 marks available. Let's have a little look. So the 3 properties that we need to consider here are obviously strength, corrosion, but also density, so how heavy it is compared to the others, because the more dense it is, the heavier it's going to be, the stronger it has to be to support its own weight. So we've got to consider that. So the answer is C, of course, because it is strong. It is not dense, so it's low density. And, of course, resistant to corrosion. If you've got any one of those 3, any 2 of those 3, you get both marks for that question. Sweet. Another page done. So, describe the metallic bonding in metals and use this to explain why most metals have a high melting point. This is a doozy of a question. Bit of a tricky one, but I've got confidence that we're going to do well in it. So if we think carefully, we can actually break this question into 2 parts. First part, describe the metallic bonding. Then use this to explain why most metals have a high melting point. So there's 2 parts to it. First off, let's describe the bonding. So we should know that metallic bonding has got close positive ions. We should also know that there's a delocalized sea of electrons. We should also know that there's very strong bonds between atoms. Okay, so that's plenty of description. The third mark, or the final mark, is to talk about the fact that lots of energy is needed to break those bonds. And that's it. That's your 3 marks. So from the outset, it looks quite tricky, but if you know your metallic bonding, then you're on to a winner. Okay? Sweet. So sodium Na reacts with oxygen O2 to make sodium oxide. Sodium oxide contains the ions Na plus and O2 minus. The electron structure, sodium, not oxygen. Use the charges of the ions in sodium oxide to work out the formula of sodium oxide. Okay, so to get your marks, you should think about, right, oxygen's here, it wants to get 8 electrons in its outer shell, so it needs to add 2. Sodium here wants to get rid of that 1 electron in its outer shell. So we know that sodium can give 1 electron to oxygen, but oxygen still wants another one. So sodium, there needs to be 2 sodiums giving an electron over. So it's Na2, because those are the 2 electrons, O, because there's only 1 oxygen needed to take those 2 electrons. There it is, 1 mark, so straightforward. If you miss it, you're a mug. Right. Use dot and cross models to describe the bonding in both sodium oxide and in a molecule of oxygen O2. You only need to draw the outer shell electrons, okay? This is our dreaded 6 marker, but you know what? If this comes up, I hope you'd be happy with this because there's some really, really easy marks available here. As usual, take 5 minutes, pause me, and have a little go, see what you come up with, and then we'll come back to it once you've paused me for 5 minutes. Okay, so pause me now. Right, well done guys. I hope you've got a diagram drawn in front of you so that we can have a little chat and a little go through it now. Now what I would usually do is show you the mark scheme, but in fairness the mark scheme doesn't have the diagrams drawn on it, and so I'm going to just draw the diagrams on here instead. So let's start with our oxygen molecule first, our O2. So if we think about it, here's our oxygen. He's currently got 1, 2, 3, come on you, 3, 4, 5, 6 electrons in his outer shell. We know that it's a pair, so here's the other oxygen. Okay, he's also got 1, 2, 3, 4, 5, 6 electrons in his outer shell as well. Now they both want to be happy, and so the reason I've drawn it like this is because they need 8 electrons in their outer shell. So oxygen number 2 has got 8 electrons in its outer shell because it's sharing 2. And oxygen number 1 has also got 8 electrons in its outer shell because it is sharing 2. That is a covalent bond. To get the rest of your marks is that you need to be able to draw me a ionic bond, okay? So it's telling us about sodium oxide. So we know that sodium, more commonly known as Na, has got 1 electron in its outer shell. Again, we know oxygen, we're going to draw him slightly differently because he's got 6 in his outer shell. Of course, because it's a dot and cross diagram, they should be dots or circles, not crosses. So we'll just go 1, 2, 3, 4, 5, and 6. Now we know that sodium gives one of his electrons over there. We need another sodium to give his electrons over there. Okay, so that's the ionic bonding. We haven't finished yet though, because you need to make sure that you draw the ions. So you know that Na is going to have a positive charge, and there's going to be 2 of them. And you know that oxygen, but with oxygen, with the negatively charged one, the one that's gained the electrons, you need to draw the electrons in the outside. So there they are. But it's going to have a 2 minus charge, and only one of them. And there's your 6 marks. Nice, easy way to get a good 6 marks there, guys. So, onward and upward. Right, water from lakes and rivers must be purified before it can be used as drinking water. Water in lakes and rivers, water purification, drinking water. Okay, I don't know why they needed to put that diagram in there, but hey-ho. There are 3 main stages in the purification of water. Write about what happens at each stage. So you need to be racking your brains. What 3 processes, what happens at each stage. So, 3 stages. First, filtration. We'll come back to that now. Second, sedimentation. And the last one is chlorination. Okay, so what happens at each stage? Filtration removes large particles. Sedimentations basically lets small particles settle out. And then chlorination kills microbes. There it is, 3 marks. Some samples of drinking water may contain traces of nitrate fertilizer. Suggest why the water purification process does not remove nitrate fertilizer. Well, of course, the reason it doesn't is because nitrates are dissolved in the water, which obviously those three processes will not remove. In some countries, there's not enough water in lakes and rivers. These countries distill seawater to make drinking water. Explain one disadvantages of using distillation to make large quantities of drinking water. Okay, so essentially, it is just that large amount of energy needed. Okay, loads of energy needed for that. So large amount of energy needed is our mark. And that, guys, is the end of the chemistry section. I hope you found that really helpful. I hope you've learned a load from that. And yeah, use it to revise as much as possible so we can absolutely smash this Unit 4 exam. Take it easy, guys. Stay classy.